Hi, good morning. Good morning, everyone. Welcome online. Welcome to the webinar organized by School of Engineering, Asia Pacific University. My name is Dr. Freddy. I'm one of the lecturers in School of Engineering. Today we have this webinar, which is one of the very interesting webinar organized by School of Engineering. We're going to speak about the emerging green technology, which is electric vehicle development, and also the charging infrastructure. I will be the moderator of today's event. And today we are very happy to have experts joining us to talk about this electric vehicle development and as well as this infrastructure for charging. So let me welcome Ali and Dr. Chi online.
Hi, hello.
Hi, Dr. Chi.
Hi, morning. Hi, everybody.
Thanks for joining us for this webinar to deliver your experience and your effort in this EV market. So maybe before we go straight to your webinar, right? Your speech. Maybe would you like to introduce yourself so that the people on the line or maybe who watch this webinar later will know more about you, and so that we can have this Q&A. They will contact you directly later.
Okay, sure.
Yeah, maybe Ali, would you like to introduce yourself first?
Okay, you can just call me Li Yuan Hao. My name is Yuan Hao. I'm actually from Multimedia University. With over 10 years of experience, we are doing electric vehicle charging infrastructure service provider in Malaysia. So we are working with brands like Volvo, Porsche, Mercedes-Benz in actually putting up the charger for their end user, also for their customers. So it's actually a very interesting thing. So we actually get to expose a lot of new technology with the partnership with them. So basically, that's how we started when we first started to build up the company.
I see. So that means you're in this industry since 2010?
We started this industry in 2013. That was when I first started the system. But prior to that, I was working with a company who actually does the electric vehicle charging infrastructure or the charging station. So that's where I get to expose the equipment itself and also the technology early on before I actually come out to actually form this EV connection.
I see. So I can say you are all in EV industry.
Yes, we are partly in the EV industry, and we hope it grows in Malaysia as well.
Sure. So we are happy for you to be on this webinar.
Thank you very much for having us.
Yeah, Dr. Chi.
Yeah, Dr. Freddy. So my name is Chi. So I'm from UC Malaysia. So I'm with a research center called Power Energy Dedicated Advanced Center, UMPDAC. So our focus is on energy-related topics. So for past 5 years, I was working with RLE. So actually, RLE has been around since the beginning of EV charging infrastructure in Malaysia. So I also learned a lot through the interaction with EVC. So basically, we see how EV has grown over the past few years. In Malaysia, it's not so much, but in the world, actually, there's a lot of progress has been done. I think this one we'll cover later in our talk. So sure. It's a pleasure to be here to share our little bit of knowledge and experience. Maybe we would like to hear there's a lot of experts in this area as well. The EV enthusiasts, they are really very much more experienced than us in many, many ways. So we also hope to get more inputs from them.
Yep.
Sure. I hope that after your speech, right, everyone is inspired and continue on promoting this green technology, right, this EV.
There's some hurdles. Later we'll talk about the hurdles as well. So there's some hurdles to get the EV.
Great. So first of all, we want to hand over this time to Ali first, who is going to deliver his very first presentation.
Okay.
So over to you, Ali.
Yeah.
Sure. So Ali is one of the director of EV Connection, Sendirian Berhad. So right now he's going to deliver his presentation. Yeah. Yeah, we see your slide, Ayali. You can start your presentation.
Okay. Good morning, everyone. Hope you all can see my slide. So today I will actually talk about the electric vehicle development and the charging infrastructure in Malaysia and what's actually the development in there. So my name is of course Lee Yuan Hao. I'm actually from EV Connection. I hope I can share some of the experience that we did in Malaysia to some of the audience outside. The first of all, we will need to go back to the basic of the introduction of vehicle classification. We actually divided into 4 types of vehicle. One of it is the ICE, or what we call the internal combustion engine. Then, of course, we had the HEV or hybrid electric vehicle. The third, it's the plug-in hybrid, or we call short form PHEV. The last but not least is the electric vehicle, which we are interested to actually know more about it. What is this HEV? Hybrid electric vehicle are those cars that you see on the road, such as Jazz, Insight, and Prius. It has a combination of an ICE engine and also an electric motor in the car. The battery capacity of the HEV is around maybe 1 kilowatt hour. It is charged mainly by the regenerative braking and also by the ICE engine itself. If you were to run on the EV range, it is actually quite limited because of the small battery capacity that you have in the car. Then we have the plug-in hybrid electric vehicle. It is quite similar with the HEV that I mentioned earlier, but the difference is it has actually a higher battery capacity compared to a HEV. The battery capacity can be in terms of 10 times bigger than a HEV. It can also be charged by an external source of power. You can actually use a portable charger to actually charge the car, or you can actually get a wall box or external charging station to actually charge it, which actually can charge it faster. Some of these PHEV can actually run on battery alone within 30 to 50 kilometers. Brands like Volvo XC90, S60, the BMW 330e, and the X5 are those examples of the plug-in hybrid which are available in Malaysia. We are looking at the electric vehicle. Electric vehicle only has electric motor inside it. Of course, it is less complicated compared to a ICE and a hybrid car. It has actually a very large battery capacity in the range of 20 kilowatt hour to maybe around 90 kilowatt hour. Charging of the electric vehicle can only be done through an external power source. Either you charge it through a portable charger, an AC charger, or a DC charger. Maybe we'll explore more on the different types of charging. The range of this electric vehicle can go from 120 kilometers to maybe 400 to 500 kilometers. In Malaysia alone, you can actually see some of the Teslas and Nissan Leaf and Renault Zoe available, which is running on the road currently. Why EV is actually developing in all those nations? One of it is India is also pushing for the electric vehicle development. Most of the problems of the countries in the major cities, they have the problem of pollution, emission from the vehicles. So India is trying to have more electric vehicles to reduce the pollution at their major cities. By end of next decade, India wants most of its cars in India to run on electricity alone, most cars to be shared, and cities to be designed for human rather than cars. They do not want to follow the Western ways of having an ICE engine, then goes to the HEV and goes to EV. They want to go straight to electric vehicle for their citizens and residents. For the third reason, they actually also want to reduce the crude oil bill that they actually import from other countries. They want to be self-reliant in terms of the energy production. Last but not least, which is very important, the grid parity. What is grid parity? Grid parity occurs when an alternative energy source like a solar PV can generate power at levelized cost of electricity that is less or equal to the price of power from electricity grid. In Malaysia, fossil fuel is still the primary source of the electricity generation, which are mostly consists of natural gas and coal. And we also have China, which is one of the biggest market in electric vehicle. They also have the same problem like India. They want to reduce the pollution in major cities. As you can see, during the COVID-19, pollutions everywhere in the world actually reduced. And China has a very good subsidy where they actually subsidize each car, EV car that you actually buy. In major cities, if you were to buy an ICE car, you will need to make sure that you can actually get, we call a tender system where you can actually get the allocation to buy it. If you were to buy an electric vehicle, you can actually buy straight away without waiting to get what we call the COE. And China has a target where they want new energy vehicle sales to be 25% of all cars by 2025. New energy vehicles consist not only on electric vehicle, but also hydrogen cars and fuel cell cars. Then we also have the grants, EV and battery to manufacturers. So a lot of startups actually try to obtain the grants from the government to actually develop electric vehicle. In countries like UK and France, they have also have a timeline to actually phase out the fossil fuel cars by 2040. By early this year in UK, they actually brought forward the diesel and petrol sales car by 2035. From the way you see that the trend is actually moving towards the electric vehicle. All countries are having a same phase out target for this. In Singapore, it's also very interesting, our neighbor. They also, early of this year, they also have a target to actually phase out the petrol and diesel cars by 2040. They do offer rebates up to 20,000 per vehicle for you to get an electric vehicle in 2021 to 2023. So this is another very interesting development in our ASEAN region. Of course, Thailand also has its own target. They want to be the regional EV hub in 5 years' time. So Thailand, Indonesia, and Singapore, they are competing to actually attract investment, manufacturing to their countries to have that kind of regional EV hub. In Indonesia, it's also very interesting. We can see that Toyota is actually investing almost 2 billion in developing electric vehicle in Indonesia. And we also seen that the news that Hyundai has also committed to do an investment up to 1.5 billion in electric vehicle plant in Jakarta. What happens to Malaysia? Previously, Malaysia has a target by 2020, we will need to have 100,000 electric cars and 125,000 charging stations by year 2020. But of course, the year of, they have actually revised the target to 2030. Many of you might be asking, so what is the rate count of the electric cars and the charging stations which we have in Malaysia currently? I will maybe explain more at the later slides. Here, the EV sales in EV and plug-in hybrid sales, you can see worldwide, it's actually increasing exponentially compared to ICE car. The biggest global EV manufacturer is going to be Tesla. You can see from the sales in 2019, they sold almost 367,000 of electric vehicle cars in the world today. And this is another very interesting information that we actually got recently. Compared to the global auto manufacturer, Tesla currently is the most valuable automaker compared to Toyota, Volkswagen Group, and all those other legacy car manufacturers. Why is that so? Since they are only making profits recently, because Tesla is not can actually contribute to actually reduce the reliance of having gas turbines or what to actually prop up the peak demand that we require for power plant. As mentioned earlier, the electric vehicle sales in Malaysia, we only have currently 200 electric vehicles on the road, about 200. But the one that is outstanding result that we have now is the plug-in hybrid. Roughly, we have about 27,500 units of plug-in hybrid running on the roads because of the incentives given by the government. What are the cars that we'll be looking to see in 2020 to 2021? Some of the cars have already been launched, like the X5 recently. They have actually upgraded the battery to a bigger battery size, where the battery itself can actually run on up to 77 kilometers, and it's actually a plug-in hybrid car. The few other cars which are very interesting that we are also working on is, one of it is the MG ES, which you can see on the bottom middle side. Is actually an SUV which is meant to be sold to mass market, because a lot of times electric vehicles are still very expensive. The next car that we are also working with is the Porsche Taycan. From here, you can see that they will be targeting to launch maybe by third quarter or fourth quarter this year. It's actually a supercar where they actually try to rival the Tesla cars, especially the Model S. Let's get technical. A lot of people does not know how much does it take to actually charge an electric vehicle or plug-in hybrid. For example, charging a plug-in hybrid car is like running a 5 horsepower of aircon. That is the actual power that it consumes or it takes to actually charge your car. So a lot of times you can say that you just plug into a 13 amp socket and let it charge. Sometimes you hear that they have horror stories of the plug point burning, the cable size melting. Those are the things that we have to actually educate and say that charging a plug-in hybrid car is actually taking high concentration of current, up to 16 amps. In some of the cars, they can actually take up to 32 amps three-phase. What are the charging modes which are available now? Mode 1 and Mode 2 are those portable charger, which you can actually plug to a normal conventional 13 amp socket. The difference between the Mode 1 and Mode 2, Mode 2 has a portable control box with a protection devices to ensure the safety of the car owners to charge the car. For Mode 3, it's actually the fixed charging stations that you see in shopping malls, petrol kiosks, and office building. You can actually a lot of users actually install this fixed type, which is more, can give you bigger power capacity. The Mode 4 is more interesting. The Mode 4 is those DC fast charger that you see on the highway. It can actually give you charging up to 80% within 15 minutes or 20 minutes time. That is those that we need quick charging, where we want to have fast charging through the car instead of waiting for hours for the charging to be completed. What are the difference between an AC and a DC charger? AC charger, like I've shown you earlier, the Mode 2 and the Mode 3, we take in input AC supply, and the output is also the AC supply. The AC and DC charger, or what we call the onboard charger, is actually placed in the car. It converts the AC to the DC before it goes to the battery. Therefore, even though your EV SE is actually higher capacity, the limitation in terms of the charging speed and the charging power depends mostly on the onboard charger. Second, we have the DC charger. From here, you can see that they take an input supply around three-phase, 100 amps to 80 amps, depending on your model and your capacity. The AC to DC inverter actually placed in the charger itself. So you can see that the charger is actually bigger in size. From then on, they change from AC to DC and go straight to the battery. That is why you are getting a faster charging, because they remove the onboard charger to the electric vehicle supply equipment. Sorry. Next, we'll be looking at the types of AC plugs which I have in the world currently. The type 1, or what we call it's mainly used for Japanese cars. Type 2 are more commonly used now in around the world. Type 3 is only used in certain countries where they have a requirement to have a shuttle protection for their charger and also plug. For DC plugs, we are also having different kind of standards in the world now. Everyone is trying to have their standards to be made as the de facto standard for DC plug. In Japan, they have actually come out with CHAdeMO DC and a plug. We also have in China where they also have their own standard called the GBT, Guobiao. In US and in European countries, we have the CCS Combo 1 and CCS Combo 2. So currently, there are still different standards available now for DC plugs, and everyone is trying to establish their DC charging system as the main system for DC fast charger. For those that have not seen the AC and DC charger, the picture on the left side is an AC charger we actually installed in a Volvo showroom. You can see the look of it. It's actually quite small in size. It can actually give you up to 22 kilowatt. For DC charger, on the right side, you can see that they have different plugs to cater for different types of cars. The number 1 plug is an AC type 2 where they can actually give power up to 43 kilowatt. Number 2 plug is actually a CHAdeMO plug. The DC number 3 is actually meant for CCS combo. For those that wants to know how does the plug actually fits into an electric vehicle, a Nissan Leaf is shown on the first picture over there. You can see from there that they actually use the AC type 1 plug. The AC type 1 plug can actually be inserted to the AC port on the socket there. Then they also have the CHAdeMO socket for you to actually charge, to do a DC fast charge on the left side of it. For a Volvo XC40, you can see that they can have a type 2 plug, which is at the top there. The CCS combo, which is, you can see the 2 pin there, is meant for you to use the DC charger. For those plug-in hybrid which has smaller battery capacity, they cannot have a DC fast charger input to the car. They only have an AC type 2 because having another DC plug will increase the overall cost of the charger, and it does not make sense if the battery is too small for them to do DC. So with the information of DC and AC charger, where are the locations that we want to install for those? Normally for home and workplace, we just install an AC charger with 3.7 kilowatt to 20 kilowatt will do. Because at home, usually once you come back from work, you will plug in your car, like your handphone. It can take up to 7 to 8 hours or 4 hours to charge. We do not need to rush the charging time of it. For commercial area, in shopping malls and in petrol stations, we want to have a faster charging. Usually, we use a 50 to 100 kilowatt of DC charger, where they can actually charge your car faster without waiting very long for the cars to reach its capacity. For highways like the North-South Highway, many times, of course, we want to have a 100 to 350 kilowatt of DC charger. It can actually charge very fast if the car can actually take in this kind of power. But the cost of building this DC infrastructure is very expensive. It costs up to $500,000 to 700,000 to 800,000 just to put one of these super fast charger at the highway. This is a spec that you can actually see for the charging duration. It's actually an XC90 spec that I'm going to show you here. From here, you can see that battery capacity is 11.6 kilowatt hour. But the battery usable is only 9.9 kilowatt hour. Not all the battery can be actually used for the driving. The other very interesting thing that I would like to show you is the charge power or the onboard charger. From here, you can see that the onboard charger for this car is only 3.7 kilowatt AC. So at the bottom there, if you were to use a 3.7 kilowatt of charging point to charge the car, it will take up to 3 hours 15 minutes. Say for example, I have a charger which can supply up to 7.4 or 11 kilowatt. Why is the time of charging is still the same? 3 hours 15 minutes. It is because the limitation, like I mentioned earlier, the onboard charger. Even though I can give you a power supply, but the car can only take 3.7 kilowatt. So it is still the same duration that you use to charge using a 3.7 kilowatt of charging station. The other project that we did with United Nations, we actually worked with United Nations with Tanchong to actually build a off-grid DC charger system at the IACRO R&R. A lot of times when you talk about electric vehicle, for electric engineers, they might be thinking, yes, it is zero emission, but you are actually polluting it elsewhere because the power that you generated to power your electric vehicle comes from coal power plant. Coal power plant, you are also polluting it and in your power plant, but just that it doesn't emit the CO2 and the nitrous oxide and everything. For this project, they wanted to showcase that charging an electric vehicle can be green. 100% of the energy generated by the solar PV system is actually stored in a battery, lithium-ion battery. The battery is used to charge the electric vehicle. Another thing that we want to showcase here is what are you going to do if the battery of the electric vehicle deteriorates and it's not sufficient for you to do daily drive. What we are trying to work with Unido here is we are trying to showcase that the old batteries from the electric vehicle can be actually used for storage system, because for storage system, 50 to 60% of your original capacity, it is still sufficient for us to actually store energy for peak shaving or for energy storage. Some of the DC chargers in Malaysia now, you can see there's a few that is installed by the dealers and also by the manufacturer. One of it is in Vision Motor. Then we can see another one in ABB's office. And the third one is actually in Nichikon's office. These are some of the DC chargers which are available in Malaysia. And recently, if you look at Paul Tan's post, you can also see that there's a few new charging DC charger which are available in IACRO, which we actually built to actually electrify the North State to make sure that the electric vehicle user do not have range anxiety if they were to travel down to outstation like Johor and Penang. Electric vehicle standards in Malaysia, I was part of the technical committee to oversee and to actually draft the standards for electric vehicle charging system. So if you are interested, you can actually go to Standards Malaysia to buy and download the standards of MS-IEC 61851 and etc. So currently, of course, we are also moving towards putting up a standard for DC charger as well. Electric vehicle charging station just give incentive or points for buildings which are going for green building index certification or other green building certification like Green RE and Green Mark. They do award point for you to put up electric vehicle charging station at your buildings or your premises. This is a typical single line diagram that we actually shown here. Basically, for charging station, you will need to have a special RCCB called the Type A to protect your charger from electrocution or leakage current. That I think I will not explain much here. What are the payment options which are available now in Malaysia? The most commonly payment option is the subscription model, or what we call you pay for 1 year, a yearly subscription or monthly subscription. You can use the charger any amount of time you need and anywhere, depending on the subscriber's model. Then, of course, we also came out with what we call the pay-per-use, the only pay-per-use system in Malaysia, where we actually work with touch and go to actually integrate with the charger to let user to pay as you use the charging station. The third option, you can actually do that by using a Jom Charge app, where you can actually use credit card to pay for the charging session. These are the payment methods which are available now in Malaysia. And lastly, I would like to focus more on this EV infrastructure ready for existing condominium. A lot of time, electric vehicle potential buyers are very afraid that they do not have EV infrastructure at their existing condominiums or apartments to charge their car. So these slides, I want to tell you what are the problems they actually face by the electric vehicle potential users which lives in those high-rise and apartments. One of the main problems that they actually face is some of these existing condominiums and apartments do not have sufficient of EV charging station facilities. Then if they do have the charging station facilities, they may only have 2 to 3 units. Some of those that park there will actually hog the place overnight, which deprives other users from actually using that facility. Then the third problems that usually we face in the existing condominiums based on our investigation and survey, the insufficient of power capacity at the lighting DB at the car park. Those DB that is at the car park is actually designed, the consultant engineers actually design it meant for lighting, not for you to charge your car. So the power capacity that they provided at the lighting DB is actually quite small. It might be able to cater for 1 or 2 electric vehicle owners installing the charging station, but the third or the subsequent user might face problem having the charging station tapping it to the existing DB. Then another question that always a lot of people will complain is the non-EV and plug-in hybrid residents will complain to the MC. Why are you using common funds to finance charging station facilities at the condo? I'm not driving one. Why should I be paying for that facility? Then we have this issue. The next issue, which is also very, very popular, there's no payment system which can actually cater for this charging at the condominiums. And some residents actually charge at their car wash power point as well in the condominiums. So what are they facing currently? So the current scenario, usually the main switchboard will have a sub-switchboard. From the sub-switchboard, you will pull another cable to your lighting DB at your car park. So the bottleneck of this problem is actually the cable size which are powering the lighting DB. What are the solutions that you can actually propose for your condominiums or your existing apartments is by pulling a new power capacity from your main switchboard to a new EV switchboard at the car park. From then on, whoever who wants an electric facility at their respective car park can actually tap from the new sub switchboard at the car park. But before you actually do this, you will need to make sure that to measure the power capacity at your MSP for at least 1 week to determine the trend and the power usage of it. From there, you can get when are they or what's the highest peak power capacity that you can actually draw that the condominium common areas actually draw. Then from there, you will divide with the design aspect of the MSB and see what's the excess power you can actually allocate for each user. This has to be done to determine the power to be distributed to each EV user. From here, you can see that we have actually done for one of the existing condominium in Bangsa. They've actually modified the switchboard to cater for the electric vehicle DB that we put at the riser. This is how the DB is located at the residence car park. From here, the residence has an individual DB to control or to install a charging station. Why do we provide an individual DB? One of it is we do not want anything, if there's any problem with the charging station or their electrical portable charger, to affect the power supply or the disruption of the common area. And planning the infrastructure is very important. If you were to let everyone just to pull individual charger to their respective parking, you will have this kind of messy wiring and conduit pipes flying out here and there at the common area. So the good thing is for the management to actually come up with a solution, come up with the cable routing where they actually install a bigger trunking for them to actually pull additional charging station or additional cabling to the respective owner's charging station. These are some of the main trunking that we did for one of the condos. We pull a trunking where each user can actually utilize the existing infrastructure or the cable routing to pull to their respective parking without making messy trunkings and pipes along the apartments. And of course, we also have the energy meters to monitor the usage of each individual to make sure that we can actually bill to the each user in terms of the electricity usage. What are the testing commissioning equipments that we actually use for doing the T&C for this charging station? We actually have a few what we call the electric vehicle simulator, where we actually simulate the fault and also the charging protocol to ensure that the charging station is able to charge not only on certain types of cars, but all types of cars, and is safe to use. With that, we also need some electric vehicle cars like Zoe and Listan Leaf for us to actually do testing for different types of plugs and standards. And lastly, we also need a standing leakage current detector to make sure that the standing leakage that is emitted from those charging stations and electric vehicle does not affect the leakage current at the overall dB. So basically, that's about all about my presentation. I hope it is clear. Maybe we can answer some of the questions later for those who want to have further information on this. Thank you very much.
Thank you, Ayali. I think we'll have a Q&A later at the end of this session after Dr. Chi.
Okay, sure.
Yeah. So now we welcome Dr. Chi online to share his part of EV. Dr. Chi, over to you. Now you can share your slide.
Thank you very much. Okay. Okay. Can you guys see?
Yeah, we hear you. We can see. It's loading. Yeah, we can see now.
Screen, right?
Yeah, full.
All right. So thank you very much, Ali, for the good introduction on the situation. So because requirement-wise, I need to explain a bit on University Malaysia. So to do a bit of marketing. So I'm from University Malaysia. So we are one of the oldest university in Malaysia, one of the 4 research university in Malaysia. And currently, we are quite fortunate to be one of the highest ranking university. We have about 2,000 plus academic staff, 21,000 students, out of which 12,000 is undergraduate, around 9,000 is postgraduate. So I'm from a particular research center called UMPDEC. So we have been established in 2010, officially recognized by Ministry of Higher Education. So our focus is very much on energy. So we used to start to do a lot of work on solar energy, power system, machine and drive, power electronics, energy policy. And in the past few years, we've been working towards electric vehicle as well. Because as what I already mentioned, the electric vehicle is actually an ongoing effort to electrify the transport sector, which is one of the highest polluting sector in the world. So when we talk about the grid, now we have renewable energy, but for transport, if we do not go for EV, the only way that we can drive the car is through fossil fuel. So that's why electrification of transport is quite important. So for my part of the talk, I will separate into 4 main sections. So the first one, I'm going to give a bit of overview on the EV trends. So I will focus not just Malaysia, but a bit on the world view. Then I will give a bit overview on the EV chargers to complement what I already mentioned. Then I will go a bit deeper into the principles of AC and DC chargers. And lastly, I want to bring your attention to something that is quite fascinating for me, which is an integrated EV charger. As what I already explained, we have a few classification of EVs. So we have hybrid, plug-in hybrid, battery, and fuel cell. So of course, when we talk about EV that currently we are aware of, usually we are talking about hybrid, plug-in hybrid, and battery. So in particular, plug-in hybrid and battery EV is the most exciting one because they are able to run fully on electric. So of course, plug-in hybrid usually relies on petrol or diesel, but you can have a full electric range of about 40-50 kilometers. And battery EV, the range can range all the way from 300 kilometers to about 600 kilometers currently. But we believe that the range is going to increase. Fuel cell is another exciting technology, but currently is still quite far away from us. Even though for Malaysia, there are some initiatives to trying to do a fuel cell. As far as we know, Sarawak already have some demonstration project for fuel cell bus. In Nano Malaysia and also in Mari, they are developing some technology that's evolving about fuel cell. So it's quite exciting to look for. But today, our talk is going to focus a lot on plug-in hybrid and battery EV because these two are the tools that requires charging from the electric charger. Okay, so we know that there's a global trend. We want to reduce the greenhouse emission. So for countries like US, in EU, or even China, so they have actually set certain targets in terms of the vehicle emission. So what they are considering is that for every year, collectively, the vehicles sold in the country should hit a certain emission target. So, but however, you cannot expect all the cars to transform into EV immediately. So they will have a mix. So a mix of EV, which has a much lower emission, and a mix of ICE car that has a higher emission. So by doing that, they can actually have an overall reduction in emission. And this can be done gradually by using EV and PHEV to slowly displace the ICE car. But if we look at the emission level, so as I already mentioned, there are a lot of people that complain EV is not zero emission. It's considered elsewhere emission. But if we look at here, on the top side, a mid-size ICE car based on the 2020 data from fueleconomy.gov. Of course, this data is based on the testing in US. Of the actual emission can vary depending on the location and the driving pattern and the weather. But this is a general guideline because all of these comparisons are done by the same body. So we can see here, a mid-size ICE car, our segment B, segment C car, will have around 250 to 300 grams per kilometer of CO2 emission. So this is a local emission directly from the tailpipe. Okay, whereas if we talk about EV, you can see that PHEV has an emission around 25 to around 150 grams per kilometers on the tailpipe because mixing of the internal combustion engine and also battery. So you still release some, but much lower than what is expected from a purely fossil fuel car. And if we have EV, we have a zero emission, no tailpipe emission, because there is no engine running, just electric car. Okay. But if we consider the life cycle means that not just the emission from the tailpipe, but also the emission created from the manufacturing, the charging. So you can see that for Europe, they make this study comparing for Europe. The conventional car, the average European car will have emission about 250 emission. So this gram per kilometers, and most efficient will be around 180 gram per kilometers. But in terms of electric, so you can see electric depends on which country you are talking about. The emission level varies. In terms of the lithium battery, and the manufacturing, which is the green and purple color one, you can see that they are more or less the same, because the manufacturing and the of the battery and the car usually is done from the same location. But the fuel cycle, which represents the emission from the power station, because you are drawing electricity from a power grid, so the fuel cycle varies depending on how green is the grid. So among the different countries, France has one of the lowest emission because of the high amount of nuclear energy that was used. So Germany used to have quite a lot, but because this is done in 2018, so around that time there was a lot of shutting down of nuclear power plant because of the Fukushima incident. So the renewable energy has not picked up yet. That's why it has a higher emission factor from the grid. But as more and more wind and solar being utilized in the grid, we expect that the fuel cycle emission is to reduce down. But for the data given in 2018, we can see that in terms of the average value, the European Union average for electric car, plug-in hybrid, is already lower than the most efficient conventional car. So this provides a huge potential. So if we can have more and more renewable energy in the grid, we expect that the number of, in terms of CO2 emission, can go further down. But it's not possible for the conventional. The efficiency that we can improve is quite limited. Okay, so we can see that how about efficiency of EV itself and the range. So when we talk about EV, at least for 5 years ago, there are usually a lot of concern. So one of the main concern is that how much I can drive per charge, which is the range, and how efficient is the system. So the efficiency has, of course, impact in terms of the range, and also it has impact in terms of the total emission, considering the grid emission as well. If we look at the evolution for 2014, the gray color one, the average point for 2014, 2018, and 2020, we show that there's a continuous and almost linear trend in terms of the efficiency improvement and the range improvement. Of course, depends on which model we are talking about, the range is different. Currently for 2020, you can see that range is around 250 to 600 kilometers for full charge. And the efficiency on average is around 5.7 kilometers per kilowatt hour. This number is targeted to increase up to about 7 kilometers per kilowatt hour by 2030. So that will bring the efficiency improvement of around 30%. So that is quite significant in terms of emission. And the range-wise, our expectation of the range is that the range will more or less saturate around 600, 700 kilometers, which is equivalent to a conventional ICE car. So this is quite interesting because for case study in Norway, for example, Norway has one of the highest number of EV by percentage. They have a certain saturation, so the number of EVs were increasing until a certain point. So when they do a study about the reason why there's a saturation, it was realized that the limitation was on the range. So for example, they were using mostly Nissan Leaf. Nissan Leaf can go about 300 kilometers on a full charge. So that restricts their travel time on weekends, whereby they usually like to travel a bit long distance. So they always use the EV as a second car. So they still keep an ICE car. So, but if you improve the range from 300 to 600, 700, then you elevate that difference in terms of long distance travel between the ICE car and the EV. Then you open up more opportunity for people to willing to switch from a normal ICE car into EV. So if you further increase the battery, there's a few disadvantages because battery is adding the weight to the car. So if you have a more heavier car, definitely your efficiency will reduce. And of course, battery constitute quite a big chunk of the cost. So if you have a big battery, the cost of the car will also increase, so which reduce the affordability of the car. So it's always a trade-off between the price and performance. Okay, so for those that are interested, there's a lot of good information provided by IEA, the National Energy Agency. So they have under IEA Electric Vehicle Initiative, EVI, whereby they have this is a forum dedicated to actually accelerate the adoption of EV throughout the world. So one of the key initiatives was EV 30 at 30, which means that they have set a target by 2030, at least 30% of new vehicle sales in the world should be EV. So this is echoing with the initiative from the many Europe countries, whereby they pledge to stop selling non-EV cars by 2030, 2035, 2040. So the current situation, so based on a report in 2020, this is quite a fresh report from IEA, we can see that the growth potential, the number of car sales, which is the bar chart, and also the market share, which is the line. So in terms of China, we know China is one of the biggest drivers for EV adoption in the world. However, in terms of percentage market share, EV is only around 5% of the total of the market share. Means that out of 100 cars sold, only 5 cars are EV. Whereas in Norway, which is one of the highest, they have really reached 56%. So almost every 1 car out of 2 cars sold in Norway is an EV. Okay, why there's a varying degree of adoption in terms of EV? So of course, if we ask you to buy an EV now in Malaysia, you might want to buy, but there are a lot of concerns. So based on the survey done in 2018, so they list down a list of main concerns that is depending on the market. So the biggest concern at 2018 was the driving range. So this echo with what the study done in Norway. So the range usually is about 300. So if you want to go for 600, like what is available in the long range Tesla, the price is much higher. So for a very affordable range, usually they consider like a Volkswagen e-Golf or even a Nissan Leaf. So this kind of car are giving you 200, 300 kilometers of range, which in most situations is only sufficient for daily commute between office and home. So you want to go a bit outstation, go a long distance. For example, in Malaysia, you want to go from KL to Penang, you might not be able to do it confidently on the car. You might need to stop and charge. So of course, the second most important one is the cost. For Malaysia-wise, the EV price is around 160, 180,000 minimum. So we are talking about BEV, so battery EV. So Nissan Leaf, Renault Zoe is around this price range. So, but Malaysia, the majority of the car purchases is targeting 140,000 and below. So because of the high pricing, so this has actually removed the potential of people switching from ICE car to EV. Then the third and fourth factors are actually related to the charging. So when we refill a petrol car, we can do it within minutes. So just a few minutes, we can have a full tank. But for EV, the charging of the battery depends very much on the charger, the power of the charger that is available, and that will translate into the time. So not only that people are worried they cannot find charger, it's not as easy to find as petrol station. They're also worried with the amount of time they need to wait for the charging to occur. So this becomes the main hurdle. So in terms of charges, we classify into 2 types, even though we have level 1, 2, 3, 4, but we are classified into 2 main types. One is a slow charger, usually it's an AC charger, and one is a fast charger, a DC charger, typically 40, 50 kilowatt and above. China is deploying the biggest amount of EV charging infrastructure compared with the rest of the world. So because of that, they are able to push the number of sales of EV much faster than other countries. So what is actually in the EV charger? So what I already explained, we can classify the EV chargers by different ways. One way is level. So this is based on the SEEJ 1772 standard. Or we can classify by mode. This is based on IEC 621696 standard. Or we can just have a general classification by the type of supply, AC or DC, which is slow or fast. So for SEEJ 1772, so the level is classified the AC level 1, AC level 2, DC level 1, DC level 2. So of course, the higher the level means the higher the power. So for EVSE mode classification by mode, according to IEC standard, we have mode 1, 2, 3, 4. So Malaysia usually we use a mode as a way of classifying. So mode 1, mode 2, mode 3, mode 4, 1, 2, 3 is AC, mode 4 is DC. So you can see that for AC, the fast charging AC is actually mode 3, and it's only around 43 kilowatt. Whereas mode 4 is DC charging. It can go 50 kilowatts, 100 kilowatts, or even now we have actually a solution by ABB who is providing 370 kilowatt. So the power level is getting higher so that we can significantly reduce the charging time, which is one of the key hurdles for EV adoption. Okay, so for today, we want to talk about it in terms of a bit simplified. So we talk about AC and DC. The AC will be mode 1, 2, 3, DC will be mode 4. So why we classify it this way? Because the AC and DC charger has a fundamental difference in terms of the way the charger works and the feature that the charger can provide. So for AC charger, okay, this is the vehicle. So AC charger is actually more like a communication device. So AC charger, for those who have taken power electronics, we know that battery is actually DC, whereas our power supply from the grid is AC. So for you to use the AC power to charge a DC battery, you need to do some sort of power conversion. Okay, this is done using power electronics. However, in the AC charger, there is very minimal amount of power electronics. The power electronics is only used to provide some power supply for the communication module. So AC charger is actually a communication module. Okay, the power device that is used to convert the power from AC to DC is actually sitting in the vehicle itself. So it's known as the OBC, or onboard charger. So this charger will be responsible for converting the power from AC to DC before you can use it to charge the battery. The battery voltage typically is around 300 to 400 volt. Of course, now with the higher performance car like Porsche Taycan, so they have 800 volt battery. Okay. DC charger is different from AC charger. The fact that the charger itself contains both communication as well as the power electronics. So instead of having an onboard charger, a charger that is onboard the car, a DC charger puts all the power electronics outside the car in the charger itself. So that's why, as what I already mentioned, the AC charger usually appears in a very small profile. So you have like a small box that can be a charger, AC charger. But DC charger usually appears as a big cabinet. So sometimes you will see just one big cabinet. Sometimes you will see one big cabinet with one small charging post. So the big cabinet will contain the high power electronics required to process the tens of or hundreds of kilowatts of power. So because that power electronics is outside the car, the DC charger has advantage of size. So the size is not limited. For AC charger, because you need to fit the AC charger into the car, you cannot build it to be too big. Okay. As a matter of fact, you can see this is the content in the AC charger. We have some protection circuit, some contactor, auxiliary power supply, and a charging controller, which is actually a microcontroller that talks to the EV. So this communication can be sent to the cloud or not, depends whether your charger is considered a smart charger or dumb charger. If it's a dumb charger, it just on and off provide the charging. If it's a smart charger, you send the data so you can do a remote control of the charging. So you can activate the charging through some apps, or you can monitor the charging status. So that's smart charger. So for AC charger, the connectors is done also by a few IC standard. So in Malaysia wise, we are using the Type 2 charger, which is on the right side. But the connectors is more or less have the same concept. We have a few power pins. In this case, we have power pins for 3-phase, line 1, line 2, line 3, and neutral, and ground. And we have two very important pins for the signaling. This is actually for the communication. So one is called the PP, one is actually called the CP. So PP stands for proximity pilot, to detect the proximity of the charger gun. And the CP stands for control pilot, which is actually the actual control signal. So if we look at the SAE 1772 standard, IEC is also using the same communication method as SAE. So we can see that the concept of using this signaling is actually quite simple. So for proximity, the purpose of proximity is mainly to detect the cable whether the cable is already plugged in or not. So this can be used to provide some sort of feature. Maybe once the cable is plugged in, you can lock the cable, or you can send a signal to the cloud telling me that, okay, it has been plugged in. And the second thing is the proximity signal is also used to detect the current carrying capacity of the cable. So as explained by Ali, there's a few different current level. It can be 16 amps, it can be 32 amps, 64 amps, depends on what kinds of power level you're talking about. Okay, but the cable, so you cannot avoid people from using the wrong cable. So the proximity is also used to detect the size of the cable to make sure that when the current flows from the charge controller, the EVSE, electric vehicle service equipment, or the charger, to the car, the onboard charger on the car, the current will not burn the cable and cause any disaster. Okay, so it's a straightforward thing. The more interesting part is the communication between the charger and the car through the control pilot. So how does the car knows whether it can take how much current? Because the car will have to talk with the charger, because each charger will be different. Some charger is maybe 3.7 kilowatt, some charger is 7.4 kilowatt, some charger is 11 kilowatt, some is 22 kilowatt. So if you are drawing too much current from the charger, you might end up burning the wiring of the charger and it cause a fire. So it's very important for the charger to tell the car how much current you are allowed to draw. So this is done through the control pilot. So the control pilot communicates with the car through two information. So one is the voltage magnitude. The second one is the duty cycle of the pulse width modulation. So if you see here, when the car is not connected, the control pilot signal measured on the charge point or the charger is going to be a bipolar. It's going to be a bipolar signal. It's going to be a signal, unipolar signal at 12 volt. It's going to stick at 12 volt positive. So once you plug in the EV charger onto the charger, what happens is that the voltage will turn into a pulse of 1 kilohertz, and the magnitude is going to be plus 9 volt minus 12 volt. So once the EV start to charge, the voltage level will change from plus 9 minus 12 into plus 6 minus 12. So when the EV requires ventilation, this is the battery is heating up, the level will change to plus 3 minus 12. So if there's something happen, there's some error on the car, so the voltage will completely collapse into just 0. So by looking at this voltage level, the EV charger will be able to know what's the status of the connection and charging, not charging, ventilation, not ventilation, or error with the car. And the EV charger will tell the onboard charger in the car how much current it can take by varying the duty cycle. Okay, so this is the operation. Okay, the duty cycle means that the on time of the pulse. So here, if we have a 50% duty cycle, it means that 50% of the time the pulse is on, 50% of the time the pulse is off, which is minus 12. And this will be plus 12 or plus 9 or plus 6, depends on what state it is in. 70% would mean that the on time is 70% and the off time is 30%. So according to SAEJ 1772, there's a relation between the duty cycle and the current that can go. So for example, that if you are going for 32 amps, so you'll get around 40 plus 50 duty cycle. So as we can see, what the AC charger trying to do is just to tell the onboard charger, okay, you can do this, you can draw this current. Then once everything is ready, you just turn on the contactor to provide the three-phase supply to the car. So it's just the only difference that you can find on AC charger is mainly whether it's a dumb or it's a smart internet connected charger. Just now we explained, for AC charger, because the AC charger has to sit in the car, it takes up valuable space. And because of this, if you need to have a higher power, the charger will automatically be much larger. So there is always a trade-off. So not only the battery, you have to size it as a trade-off between performance and cost, but the charger is also a cost of space. So typically we can see that the charges is around 3.7 kilowatt to about 11 or 16 kilowatt. So it doesn't go anything higher than that because of the size constraint. For example, this is Mitsubishi iMIF. This is the layout. So if you look at the back trunk, the onboard charger itself already take half the space. So the other half is the ECU, electronic motor control, which is also the inverter. So you take almost the same space as the inverter. So that is not that is only for around 7 kilowatt of charging. So you want to have a bigger charger, then you need to have more space. So this become a big hurdle for the onboard charger. And onboard charger, if we if we look at it, apart from onboard charger, in the EV actually we have a battery, electric motor controller or inverter, which basically is the AC and DC control, and we have electric motor. So this is the main drivetrain of an EV. So when we want to drive the EV, power will flow from battery into the motor through the inverter. And when the motor breaks, when the car breaks, more power will flow from motor to the battery through the inverter. So it's a bi-directional converter. Onboard charger will sit in by putting another stage. It can be a single stage or two stage. Usually it's 2 stages of power electronics to the battery. So usually it has a power factor correction and a DC-DC converter. So a power factor correction will convert the AC to DC, usually through some sort of rectifier. And then the DC voltage will be controlled using a DC-DC converter to charge the battery. So this is onboard charger. So just now in the Mitsubishi, we can see that on the left side, there's one box. So that will be the onboard charger. On the right side, there's another box. That will be the DC-AC converter. So these are some of the typical charger topology. It can be a direct rectifier with a buck converter. It can be interleaf buck converter. It can be a resonance DC-DC converter, dual active bridge. Doesn't matter. Yeah. If we see the commercial vehicles, the commercial EV, the onboard charger, the size is usually much smaller than the inverter size in terms of power. For example, for Nissan Leaf, the power of onboard charger is around 6.6 kilowatt for the first version. Then the power electronics, the converters to drive the motor, is actually 80 kilowatt, because you need to have huge driving power to drive the car. But you want to reduce the size of your charging, you can have a slower charging, just taking longer time. But when you drive the car, you need to give that power to drive that car at high speed. So you need to have a high power. So you can see that there's an unbalance in terms of the power. Okay. What is done in DC fast charger is that instead of relying on the charger on board, if we take out these power factor correctors and DC converter and put it outside, we can make the size much, much bigger. So the power can go from 7 kilowatt to hundreds of kilowatts. And this is usually done by using multiple modules. So one module, let's say 50 kilowatt, maybe you can have 5 modules of 10 kilowatt DC converters. Then you can achieve the power. So for bigger system, 100 over kilowatt, you might have an individual module of 50 kilowatt. You can have 3 of them, you can have 150 kilowatts. Okay, for example, this is from ABB. So the one that we install for Porsche. So it's Terra HP. So they have 175 kilowatt of power. So if you go to any of these chargers, you actually mainly see this small and very slim charging post, the charge post. There's near the parking for you to charge the car. So this is quite small, but this is actually just the communication. The main part, the main power electronics that process the power and the transformer will be in a separate cabinet that is 3 or 4 times bigger than this charge post. And it's usually located somewhere a bit hidden so that it's visually pleasing. But this is a common way to do it. So you have a big cabinet to store this 175 kilowatt worth of power electronics. Because DC fast charger can have power 20-30 times higher than the AC slow charger. So it's very natural that the speed of charging will be much faster. And we know that people nowadays, we do not have a lot of patience. So we want things to be done fast. If we cannot reduce the charging time from hours into minutes, then we will hit a hurdle in order to encourage people to use EV. So do you want to drive an EV from KL to Penang? So the journey itself will take you 4 hours, but halfway you might have to stop at Ipoh to wait for 2 hours to get your car charged. So the whole journey will be 6 hours. So it just doesn't make sense. So what you might want to do is you want to drive and maybe stop at Ipoh for a quick meal, do a 15 minutes charge or half an hour charge, then continue up to Penang with a lot more battery left. So this can only be done by having a DC fast charger. So more and more cars that are being introduced are equipped with DC fast charging. Now here I must highlight, not all the EVs can do DC fast charging, because for DC fast charging, you need to be able to access the battery directly. So if we look at this configuration, you must have 2 connectors that goes directly to the battery, and you are not giving the power supply, AC power supply directly to the car. You are giving a DC power supply to the car. So the connection is a bit different, and the battery must be able to take that extremely high amount of power. So not all the cars are equipped to take DC fast charger. So now we can see more and more cars are being built to take DC fast charger, because that will significantly reduce the charging speed, the charging time. So there are a few different charger for DC fast charging, depends on which part of the world. So the main one that we have is a CHAdeMO from Japan, and CCS Combo from US or Europe. Of course, China is having their own system, the Guobiao, the GB, which is also getting more and more popular because they are one of the key players. But for most of the Japanese cars, they are using CHAdeMO. For most of the European cars, they are using CCS Combo. So fast charging, so this is what we mentioned, you require to have ability to take fast charging. So what is actually fast charging? Fast charging means that you must be able to take the power higher than 1C. So for those who have worked in battery before, we know that battery, we have to consider the ampere hour. So if for handphone, when you buy a handphone, you know that we are buying 4,000 milliampere hour. We're not buying a bigger battery, 6,000 milliampere hour. So 1C, if you buy a 4,000 milliampere hour, which is 4 ampere hour, if you want to charge it at 1C, means that you are charging it at 4 ampere. So 4 ampere hour, 1C is 4 ampere. Most of the battery, you should not charge it more than 0.3C. So if it's a 4,000 milliampere hour battery, you should charge just 1,200 milliampere hour max. Otherwise, you will spoil the battery. So if you want to do fast charging, you must be able to charge it at 1C, 2C, maybe 5C. So the battery must be designed to be able to take it. So this is some of the standard for fast charging. Okay. So just now we talk about the charger. So we have AC charger, we have DC charger. The advantage of DC charger is that I can have a higher power converters to squeeze the amount of power into the battery at much faster speed. However, if we look at the EV, we know that the EV inverter itself is also high power. So if we can use the inverter as part of the charger, then we might be able to reduce the size of onboard charger. So this is being done by Renault Zoe. So in Renault Zoe, they have a charger called the integrated charger, which they call it the chameleon charger. So in the advertisement, you will see that this is what they advertise. So if you use a DC fast charger, 20 kilowatt, it requires a space of 1 meter cube for the 20 kilowatt DC converter. But when you use their AC chameleon charger, it only requires 0.03 meter cube of space. So this doesn't make sense because you can process twice the higher power at a fraction of the size. Okay. What was done was that actually the chameleon charger was not the real power electronics. It's actually just part of the charger. So just now we talked about this topology. So in normal operation, when the car is moving, we're drawing power from the battery to the motor through the inverter. So this inverter is usually sized at high power. And this inverter, because we want to be able to recover the energy from the braking, we usually has a bidirectional power capability. Power can flow from battery to the motor and from motor to the battery. So the integrated onboard charger, what they do is that they provide some sort of circuit that allows the AC power to be plugged in, and the power will flow through the motor, which is designed to take high power, and the inverter, which is designed to take high power as well, into the battery. So these two stages is already designed to take much higher power, which is like, for example, for Nissan Leaf, the first generation is easily 80 kilowatt. You can take 80 kilowatt of power. So they can provide this 80 kilowatt power easily. So you just need to find a way to bring the AC power through the motor without creating rotation in the motor. The main problem is that you must make sure the current flow through the motor doesn't rotate. So when you charge the car will not run away. Your car will remain stationary at the charging station, and you can charge the car through the motor. So why do we want to charge it through the motor? Because a motor is actually inductor. So if we have power electronics, when you want to do conversion from AC to DC, from DC to AC, or even DC to DC, you always need to have inductors. And inductors is one of the bulkiest and most space-consuming parts in the converter. So we want to reduce the size of a converter, we have to reduce the inductor. So in this onboard charger, they completely eliminate the need to have inductor by using the inductance in the motor. So this is quite an interesting topology. So this is a patent. For those that are very interested, you can search for this patent. It's patented by Renault in 2012. It was granted 2012. They describe how they're using a current source converter at the front end through the motor and through the inverter to charge the battery. So they actually have found a few patents on this. One is on the topology, how the structure of the converters is structured. One is a method of controlling, and they have a few more on how to control it to reduce the leakage and things like that. Okay, I think I'm a bit over time, so I'm rushing over. So that's all from my part. I think we can open for Q&A.
Okay, thank you, Dr. Chi, and thank you, Ali, for your insight. I think it give you an overview of the EV development, not only in Malaysia, but all over the world. But let me first pull out some questions from the floor. Okay, address. Okay, this is one of the interesting questions. I believe that maybe in both of your presentation you have addressed this, but let's see. Okay, this is one of the you can see right from the screen.
Yep.
The question says, sir, I am a bit confused here. Now we can reduce the carbon dioxide pollution by moving towards EV, but EV works with electricity, and to produce electricity, we still need to burn fossil fuel. So burning fossil fuel also increases pollution. So what really is the benefit of EV to the environment?
So now you want to talk about this?
Maybe you can talk about the efficiency aspect on the ICE car and the electric motor, induction motor. So maybe I will be talking more on the, because if you see our pollution-wise in terms of efficiency of the cars, an ICE car compared to an electric car, electric vehicle efficiency is still much better compared to an ICE car. But the other thing that we cannot be doing, or we might be doing, is by generating energy from renewable energy. As you know, our government is pushing 25% of the generation of electricity from renewable by 2025. So in a way, it will reduce eventually. But if you were to stick to driving an ICE car, the level of emission will still maintain the same or keep increasing with the number of ICE car increasing. But if you were to drive the electric vehicle car and the generation of renewable energy in our country is actually increasing, you actually get a lower emission over time. That is my my take on this, but maybe Dr. Chi can add further.
Yeah, exactly. I think what I only mentioned is spot on. So EV cannot be done individually. So electrification of transport has to be done concurrently with renewable energy. So that's one thing. The second thing also, using this electric vehicle also opens some new opportunity in increasing renewable energy. So one of the things we know that renewable energy like solar or They are highly intermittent, so we cannot control them. So sometimes we are generating more than we can use, and then we have to just turn off the wind turbine, or we turn off the MPPT, so that we don't maximize the solar energy produced. So with EV, electric vehicles is always embedding battery. So when the EV numbers become a lot, what happens is that we have tons of batteries readily connected to the grid in a distributed way. So that's why there's a lot of talk about V2G, vehicle to grid. Instead of taking power from the grid, electric vehicle can also provide power to the grid. So what they do is that they can take out power from the renewable energy like solar. When there's too much solar, not enough consumption, they will charge it into the car. And when there's not enough solar, the battery from EV can actually discharge and support the grid. So there's a lot of new opportunity associated with EV. But the prime concern is that you must increase renewable energy, and you cannot just burn fossil fuel.
Yeah, thank you. I think it's quite straightforward. Your answer is quite straightforward and clear. Let me pull out another question from the floor. And this is asking that for mass implementation in countries such as Southeast Asia, right? Thailand, Malaysia, and Singapore, how do you see AC versus DC, taking into the account of existing electrical infrastructure readiness?
I'll take on this. Okay, for us, like in Malaysia, Singapore, and Thailand, we are also facing the same issue. Putting up a DC charger will require you to upgrade the electrical infrastructure. If you are not able to upgrade, of course, we will need to do some measurement before we decide whether there's excess power for you to actually put up the charger for that thing. If the charger has not enough the power source from the infrastructure, then we'll need to upgrade it. But that is the last resort that we will do, because upgrading an electrical infrastructure will even make your return on investment of putting up the EV or DC charger even less attractive. That is the things that we will need to consider before we actually plan out the AC or DC charger.
What do you think about in Malaysia context?
In Malaysia context, we see that most of the places will have a limitation or a constraint on the existing infrastructure. It depends on the cost of pulling a new, upgrading or pulling a new electrical infrastructure to make sure that the power capacity is able to put up the additional load that you'll be putting into the system. So in any way, everywhere also you will face this problem, not only in countries like Malaysia, Thailand, or Malaysia. In US or in Europe, they also have to pull a new infrastructure line to cater for their supercharger. So I think there will be no difference in Malaysia or Thailand side. It's just that how cost effective can you build a charging station?
I see. Okay.
We spoke with people from TMB. So for them to install an AC charger is just like installing a high power aircon. So the process is almost similar. So there's not much difficulty. Just that you make sure the sizing is done correctly. For DC charger is a bit more tricky. You might require an upgrade of transformer. So selecting proper size is quite important. So whether you want to go really all the way up to 370 or 175 kilowatt, or you just want to have a 50, 60 kilowatt system. So the one depends on the trade-off between your infrastructure cost and also your performance of your DC charger.
Okay, taking on to what the floor has asked, right? Let me also add on to some of the question. I think since you are saying that this AC/DC charging infrastructure is one of the hurdle, right? And also EC also have different types, different connectors. Charging time is also one of the concern. Furthermore, the owner also perhaps need to buy bear some of the facility cost, right? So would you think it is quite inconvenient for one to have EV on the road, or what do you think the solution moving forward?
For landed property, I think it's quite straightforward. If there's a will, if the owner wants to have an electric vehicle, definitely household takes up maybe 90% of your time of charging. Maybe 10% is only for public charging and etc. for condominiums apartment, that is the worry that we are actually facing, because in Malaysia, there's no regulation which allows the user to install the EV charging station. They are very much dependent on the joint management body and the MC to allow the user to install it. So different condos have different requirements and different perspective on this. So Malaysia have to have a guideline where the user has, the MC or GMB has to allow anyone who wants to put up an EV charger at their apartments or condominiums. That is one of the main things that we will be advocating.
I see. So okay, taking into this, right, just now in the presentation by Dr. Chi also mentioned that Norway has one of the highest market share in terms of EV, right? What do you think Norway have done, you know, so in such a way that their EV has such a high market compared to other countries, perhaps like compared to China or maybe even in Malaysia?
Wise, they started very, very early. So the EV encouragement policy goes way back to the 1990s and early 2000. So they have policy that roll out stages by stages and they keep reviewing it. I think a few key concerns was that early adopters, usually there are people who are more green conscious. So there are people who are aware and they want to go green. So Norway, I think Norwegians region, they have this advantage. And they were giving a lot of perks like a lower tax, lower road tax, the rebate. So for Norway, the EV price is equal or cheaper than ICE car, equivalent ICE car for quite some time. So for my personal view is that the price is always the prime concern. So currently the technology is more or less matured. Of course, there will be some worry on reliability and replacement. But if the selling price itself doesn't meet the same point for equivalent model, then it's not going to happen. So taking Malaysia, for example, we saw a peak in PHEV, plug-in hybrid, back in 2016 to 2018. So that time, there was rebate given to the plug-in hybrid, and the price of plug-in hybrid was actually cheaper than the equivalent ICE car, like for the BMW. So some argue that it's not completely equivalent. For example, we have BMW 330e and 330i. So in terms of the engine size, it's slightly different, but they are at least on the same class. It's a BMW, same brand, and it's a 3 Series. So if you are cheaper, then people will start to consider. So for Norway, they already break that parity point for quite some time. So they are no longer considering whether I can afford or not afford. So it's almost as affordable as ICE car, and they give them more convenience. They can have priority parking, they have the waiver of many things. So that's why it's easy for them to push. So for our side, because our purchasing power is a bit low, so currently the price of the car is still expensive. But we are seeing a trend, reduction trend. For example, Nissan Leaf back in 2012, the selling price was around 180,000. So currently it's about 190,000. So almost the same. But the battery size of the Nissan Leaf has increased by double. So we know that battery price is one of the key costs of the EV. So if you double the battery size, but your price remains the same, actually your effective price of EV has reduced. So as the price of battery continue to go down, we can see more and more competitive price coming out. Maybe Ali can explain a bit on the price side that you can see.
For which one?
For EV, what do you see as affordability?
So I see in India or in China, you can actually find electric vehicle at a price range of 50,000 ringgit to 60,000 ringgit. There are also plans from the auto manufacturers here to actually bring in those cars, which can actually drive up to 100 to 150 kilometers, which is meant for you to use for daily use. So we will reach to a price parity very soon, depending on the, of course, when you bring in those cars, our CPU tax and the excise duty is actually very high. It depends very much on our government's initiative to push for this green agenda.
Okay, so you are saying that actually one of the success key we can taken from Norway is because one of the things is, of course, they are more aware and conscious about green environment. The second primary factor is cost and price, isn't it? So what I can say, maybe government play a very important role in this to ensure and to promote electric vehicle, right? Or maybe can I ask any initiative right now taken by Malaysia government or perhaps from industry side to convince or to discussion with Malaysia government?
One of the things that vehicle manufacturers are looking at is whether the infrastructure in terms of the EV chargers are ready at the places or not. Because they do not want to bring in, it's a chicken and egg issue. They do not want to bring in or import in their electric vehicle because in Malaysia, the infrastructure is not ready. Then the other thing is people are not investing in putting up EV chargers and the infrastructure because there's no car to actually convince them that putting up the chargers will have a return on investment. So it's actually a chicken and egg thing. So it will actually take some time before the market matures and people see there's a potential for you to bring in the EV cars and for you to build more EV chargers and for the government to see that there's actually more benefits in terms of job creation and investment to actually invite or give incentive for those electric vehicle manufacturers.
I see.
In Malaysia, you can, for those who are not aware, they actually provide electric vehicle in green investment tax and allowance for people who buy charging station for companies. As long as your product is listed in My Hijau directory.
I see. So thank you, and thank you for the clarification and answer. I think we pull out one or two questions. Yeah, I think this is one of the a little bit technical. Let me pull out this one. It says that question. I believe this. Maybe he's doing charging now. Any suggestion on the best charging algorithm for vehicles, or maybe what is the standard to regulate charging? What do you foresee the future in vehicle charging technology in reducing the charging time?
Okay, so I'll try to answer this one.
Okay, sure.
I'm not such an expert on the charging algorithm, so there are quite a number of researchers doing on this one. Okay, but what we have been doing is usually we are using the 2-state or 3-state charging method. So this is quite standard. Even just now, if you can see the slide on fast charging, so there are some patents even by Tesla. So they are using 2-state charging. 3-state charging. So the 2-state charging basically is you have a constant current charging and constant voltage. So because we need to comply to two constraints. One is the current cannot exceed the limit because of the ohmic losses, heating of the battery. And the second one, the voltage cannot exceed the limit because of the electrochemical potential of the chemistry. So they'll try to give the maximum current where the voltage is low. So once the voltage hits the limit, then they will taper off the current to keep it at the maximum voltage. So that is typically the method. So there are some people that use some pulse charging and something, but there's not really significant improvement. But I think in 2018, there was some work done by MIT. So what they were doing is that they were trying to correlate the charging with more on the mechanical and chemical characteristic of the battery. So for battery, when you charge it at a very high current, you will cause the electrode to saturate, and then they will form some sort of dendrites, like spikes. So if you charge it too fast, what happens is that the formation of this structure might penetrate the electrode, or it causes a shorting. So how do you control the charging rate so that you do not create that by controlling the temperature as well? So there are a lot more studies. So nowadays the study is moving towards multi-dimensional. So we're not just looking at electrical, but you have to look at electrical, mechanical, and chemistry. I think that is the direction for charging.
Sure. I think thank you, Dr. Chi and Ayali. I think because of the time, right? I think now is your lunchtime as well. I think I want to encourage, if you have any other question, you can leave it on the comment. I will pass to the speakers. Yeah. And just for your information, right? When the speakers mentioned about ICE is referring to internal combustion engineer. Okay, so that's the definition of ICE. Okay, thank you, Ayali and Dr. Chi. So this will be the end of our webinar. We're gladly to have you in this webinar, and I believe many will be benefited.
Sure.
Thank you,
I hope
guys.
Get something from the presentation. Thank you very much again.
Thank you so much. All right.
Thank you.
Okay, bye.
Bye.
Bye.